wine model had an R-squared value of 0.83, which tells us how accurate our model is on the data we use to construct the model. So we know that our model does a good job at predicting the data it has seen. But we also want a model that does well on new data, or data it has never seen before, so that we can use the model to make predictions for later years. Bordeaux wine buyers profit from being able to predict the quality of a wine years before it matures. They know the values of the independent variables, age and weather, but don't know the price of the wine. So it's important to build a model that does well at predicting data it's never seen before. The data used to build the model is often called the training data, and the new data is often called the test data. The accuracy of the model on the test data is often referred to as out-of-sample accuracy. Let's see how well our model performs on some test data in R. We have two data points that we did not use to build our model in the file winetest.csv. Let's load this new data file into R. We'll call it winetest and use the read.csv function to read in the data file wine_test.csv. If we look at the structure of winetest, we can see that we have two observations of the same variables we had before. These data points are for the years 1979 and 1980. To make predictions for these two test points, we'll use the function predict. We'll call our predictions predict_test and use the predict function. The first argument to this function is the name of our model. Here, the name of our model is model 4. Then we say new data equals the name of the data set that we want to make predictions for, in this case, wine test. If we look at the values in predict test, we can see that for the first data point, we predict 6.768925, and for the second data point, we predict 6.684910. If we look at our structure output, we can see that the actual price for the first data point is 6.95, and the actual price for the second data point is 6.5. So it looks like our predictions are pretty good. Let's verify this by computing the R-squared value for our test set. Recall that the formula for R-squared is R-squared equals 1 minus the sum of squared errors divided by the total sum of squares. So let's start by computing the sum of squared errors on our test set. The sum of squared errors equals the sum of the actual values, wine test, $price, minus our predictions, predict test, squared, and then summed. The total sum of squares equals the sum, again, of the actual values, wine test, price, and the difference between the mean of the prices on the training set, which is our baseline model. We square these differences and add them up. To compute the R-squared now, we type 1 minus the sum of squared errors divided by the total sum of squares. And we see that the out-of-sample R-squared on this test set is 0.7944278. This is a pretty good out-of-sample R-squared. But while we do well on these two test points, keep in mind that our test set is really small. We should increase the size of our test set to be more confident about the out-of-sample accuracy of our model. We can compute the test set R-squared for several different models. This shows the model R-squared and the test set R-squared for our model as we add more variables. We saw that the model R-squared always increases or stays the same as we add more variables. However, this is not true for the test set. We want to look for a model with a good R-squared, but also with a good test set R-squared. In this case, we would need more data to be conclusive, since 2 data points in the test set are not really enough to reach any conclusions. However, it looks like our model that uses average growing season temperature, harvest rain, age, and winter rain does very well in sample on the training set, as well as out of sample on the test set. Note here that the test set R-squared can actually be negative. The model R-squared is never negative because our model can't do worse on the training data than the baseline model. However, our model can do worse on the test data than the baseline model does. This leads to a negative R-squared value. But it looks like our model, average growing season temperature, harvest rain, age, and winter rain, beats the baseline model. We'll see in the next video how well Ashenfelter did using this model to make predictions.